Hello everyone, welcome to the sixth video on Simulink model for electrical circuits. In this video, we are going to discuss about, or we are basically going to implement the Simulink model for single phase full wave controlled rectifier. So in the last video, we have seen the single phase half wave rectifier we have implemented in Simulink. Now this time, or in this video, we are going to implement the full wave controlled rectifier. Now, to implement this full wave rectifier, we will need 4 thyristor. Okay, so basically your full wave rectifier will rectify, or it will kind of convert the negative cycle to a DC, okay, or to a positive voltage or a constant voltage, near about constant voltage with ripples. So basically the question, it says you have to build a Simulink single phase full wave rectifier circuit connected to a 100 volt Vmax 50 Hz supply and a 10 ohm load. Okay, so in the figure I've used RL circuit, but we have to use 10 ohm, that is a resistance only load, and we have to measure the output voltage, the average output voltage, and compare with the calculated values. Okay, so now let's go on to Simulink and try to implement this circuit. Now, to implement this circuit on single phase full wave controlled rectifier, the first thing we would need is, as always, the AC voltage supply. Okay, so this voltage, the the peak value is given as 100 volts, so we don't need to change the value, but the supply frequency is 50 Hertz. Okay, so I can change that, and I can turn on the block names, right? And then I will need 4 thyristor. Okay, so let's look for the thyristor. Usually it is at the bottom. Okay, now I will need 4 of them. So what I'm going to do is I'm going to rotate it and arrange it in a certain way so that I can connect all the other thyristors. Okay, so I've rotated it 2 times. Okay, now let's copy it and paste 4 of them, or 3 more. Okay, something like that. Okay, so uh, the anode of one thyristor, I'm going to connect it to the cathode of the bottom one. Okay, and the same goes for the second pair of thyristors. Okay, and the cathodes, I'm going to connect them something like that. Okay, and the anode to the anode. Okay. Now the supply voltage. So the positive terminal, I'm going to connect it to the first pair, and the negative terminal, I'm going to connect it to the second pair, like that. Okay. Okay. Now the next thing I need is a pulse generator. Okay. So I will use a single pulse generator to trigger all the thyristors. Okay. So the gate terminal is here. So we can connect the pulse generator to the first one, and this is the gate connected to the second one. I can connect the gate again, something like this. Okay. Alright, so before going further, let us now set the value of this pulse generator, or the parameter of this pulse generator. Okay, so the amplitude will be 10, the period it will be 0.01 seconds, the pulse width it will be 10, and the phase delay will be, again we'll use the same variable, angle, divided by 360 multiplied by 20 e to the power minus 3. Okay. Now again I'll have to measure the uh, the voltage and the currents. So let us now connect a voltage measurement block. So the first thing I need to measure is the voltage across the load. The next thing I need to connect is a resistive load. So let's search for series RLC. Let's rotate this one. Okay, and turn on the block name. Okay, so this is my load resistor, and its value will be 10 ohms. So R equals to 10 ohms. Okay, and change the parameters. So resistance of 10 ohms. Okay, now I need to connect it between the uh, thyristor pair. Okay, so you can connect it, but one more thing I will add is a current measurement. Okay, so I will add a current measurement block here before making the connection. Okay, so this is my current measurement block here, and it will be connected here between the thyristor pair and the load resistance, and another one will be connected across the anode. Okay, then I need to measure the voltage across the load resistor. So I will copy this and paste it So this is my load voltage and this is my supply voltage. Okay, let's connect it. Okay, and again similar to the last circuit, I will measure the average voltage or the mean voltage. Okay, so let's search for the mean block, this one. Okay, and change the fundamental frequency to 50 hertz. Okay, now I will have to measure the supply voltage and all these things, the supply current and the pulse generator output. So for that I will search for display and add a scope. Okay, so this scope will again need three uh, inputs. Okay, so let's change the number of input ports to 3. Okay, so let's see, this is my current. Another thing I will need is, let's connect it to the voltage, and the last one to the uh, pulse generator. Okay, now I will need to display the number, the average voltage as well. Okay, so let's search for the number display, and right, so this is my average or RMS, sorry, the mean voltage, mean or average voltage. Okay, so near about I've connected all the blocks which I needed. So the last thing I need is the power GUI block. So let's place it here. Now the last thing which I need is, I need to set the value for the variable which I'm using. Okay, so let's set it to 10. Okay, now let's run the circuit. So for 10-degree firing angle, the average voltage is coming out to be 61.23. And let's check the waveform. So we need to change the stop time. Okay, currently it is 10 seconds. So we can change it to 0.06. Okay, and run it again. So again 61.35. Let's check the waveform. We can display it on three different plots, and change the style or the color to maybe red, and this one to blue. Okay, I have to apply it, right? And the last thing is turn on the legend. Okay, now so this is the uh, output, the current, and this is the supply voltage and the pulse generator output. Okay, now we can run this circuit for different firing angles. We can change the value of angle. Another thing which I wanted to do or implement in this circuit is to measure the total harmonic distortion. So let's say if I want to check the total harmonic distortions uh, for different firing angle. So what we can do is we can search for THD block, total harmonic distortion. Okay, and along with that I will need a gain block. Okay, so the total harmonic distortion, I need to change the fundamental frequency. Okay, and a display, so I can just copy this one and connect it hopefully here, and this is my total harmonic distortion in percentage, DHD in percentage. Now I just need to check if I have changed. Okay, so you have to change the gain to 100, okay, to calculate the percentage. And where is my current? Current is here. Okay, so I've connected it to the current measurement or after the current measurement block. Okay, now I have to change the fundamental frequency to 100 hertz. Okay, so for full wave rectifier circuit, the fundamental frequency should be 100. Okay, now let's run the circuit to check the output. Okay, so total harmonic distortion, it's coming out to be 25.25% for 10-degree firing angle. Now let's change the firing angle to, let's say, 45 degree, and run the circuit again. So as you can see, the total harmonic distortion, it increased to 34.9, and the mean average voltage, it reduced. Okay, 53.09. If we check the waveform, as expected, uh, the the output from the thyristor or from the full wave rectifier using thyristor, it depends on the firing angle. Okay, so as we increase the firing angle, the rectification process will start after the corresponding delay. Similarly, let's change the firing angle to 90 degree, and let's check the last one. So the total harmonic distortion, it increased to 57.5, and the average voltage, it reduced to 31, and waveform is as expected. Okay, so basically by changing the firing angle, we can increase or decrease the average output voltage, and also the total harmonic distortion will change. Now coming back to the slides to verify our measurements using calculations. So we can use this formula to calculate the average voltage from a full wave controlled rectifier. So I have already calculated it for all the different firing angles, and as you can see, there is a slight difference. So the calculated value is slightly higher. The reason for that I have already explained in the previous video. So it's mainly because of the thyristor. Now looking at the outputs for different firing angles. Uh, so this again we have discussed in the previous class as well, and while discussing the circuit. So as we increase the firing angle, the uh, rectification, it happens or it is delayed. Okay, so this is all that I wanted to discuss in this video, and in the next video we will discuss or try to implement a three-phase full wave controlled rectifier circuit. Okay, so hope to see you in the next video.